Yay!
Yay! Okay, now let's look at examples of capacitors in a circuit, and let's see how to calculate some circuit quantities. Let's suppose I've got this little circuit hooked up to a 28-volt source, and all just to keep things easy for now, and you'll see how you can change it. All capacitances here are 4 microfarads, let's say. They're all identical. So let's find the charge stored on each and the amount of voltage dropped across each for this circuit. For each. Okay, the first thing to do, this is like what we do in circuits. The very first thing, our step A, find the equivalent capacitance of that whole network. So just pretend we're going to try to boil this whole thing down to one capacitor, because that's what the battery sees, right? The battery has no idea how everything is arranged. I mean, it's a battery. It doesn't have eyes or whatever. So it has no idea how these things are arranged. All it knows is that there's some capacitance for the entire circuit, and that's what it's responding to. So let's figure out what that is. And the rules are capacitors in series. It's opposite to resistors, all right? So in series, the equivalent capacitance is just 1 over C1 plus 1 over C2 plus however many you've got in series, and then you just flip it at the end. That's like resistors in parallel. So for example, the first thing we ought to do, notice that C1 and C2 are in series with each other. So let's boil that down to one capacitor. So the equivalent C12 capacitor is just going to be 1 over 4 plus 1 over 4 minus 1. What is it? A quarter and a quarter. That's going to be a half. And then you flip it, and that's going to be 2 microfarads. So we could replace C1 and C2 with just one 2 microfarad capacitor, and the circuit is going to behave exactly the same way. Okay, and then I've got C1, C2. I've got that in parallel with C3. And the other rule is, in parallel, the equivalent capacitance is just, you just add them together. So C1 and C2 together make up a 2 microfarad. C3 is a 4. So the equivalent C123 is just 2 plus 4, or 6. Okay, so now we've boiled that upper network down to one capacitor, one equivalent capacitor that's 6 microfarads. And now that's in series with the final one, C4. So then finally, C1, 2, 3, 4, I'm just going to add those together in series. So that's just going to be 1 over 6 plus 1 over 4. I'm leaving off the microfarads because we're going to throw that in at the end. Minus 1. 6th and a 4th. What is that? Well, 1/6. What is that? 2/12. A quarter is 3/12. So that would be 5/12. And then you flip it, 12/5. So that's like 2 and 2/5. So that's like 2.4. Okay. So the equivalent capacitance of that whole that whole network, that whole circuit, is 2.4 microfarads. That's what the battery sees. All right. So now what I can do is I can figure out how much charge is stored in the whole circuit. So the total charge stored, that's pretty easy. That's just going to be C times delta V, right? So that's just going to be C equivalent times delta V from the battery. So that's just going to be 2.4 microfarads times 28 volts. And if you do that, you get, what did I do? I got like 67.2 microcoulombs. Okay, So that's the total amount of charge stored in the circuit. Now, there's a couple of things that we can use to sort of detective our way around the circuit and build up our answer. If I know that the total amount of charge stored is 67.2, that helps because remember, maybe you've seen this in your book, in series, let me write this down in here, series, the charge stored on one capacitor is the same as the charge stored on the next capacitor. The reason for that is because if I have capacitors in series like this, where one is like plus minus, then this one's got to be plus minus. Look at this. Right? One of those is plus and one of them's minus, but that's all sort of the same piece of metal. I'm connecting one plate with another with a piece of metal. That's all got to be the same amount negative charge on one side as positive on the other, because this thing didn't start out charged. This thing was just a neutral piece of metal before I hooked up the battery. So if I pull a certain amount of charge to one side, it's got the same amount of charge that's positive on the other side. And so the total amount has to be balanced. And then what that means is if I've got a plus here, that it induces the same minus charge on the capacitor across the gap, which is the same as that plus charge, right? So capacitors in series have to have the same amount of charge all the way through the series. Okay, so if the charge is the same in the series, that means that the charge on C4 is going to be the same as the charge on the C123 kind of little sub-network up there. So I can just say right away that this has to be the charge on Q4. And then look at this. If I know the charge on Q4, now I can figure out what the voltage drop across Q4 is. Because the battery, like C4 doesn't have all that voltage across it, because then there'd be nothing left for C1, 2, and 3. So how much voltage is across C4? We can figure it out. V4 is just going to be Q4 over C4. So that's going to be 67.2 microcoulombs over, what was C4? C4 was, it's just 4 microcoulombs. And when you put that in a calculator, you should get 16.8 volts. There we go. So I know the battery is delivering 28 volts, and I know there's 16.8 volts across that C4 capacitor. All right. So what that means is that the rest of the voltage has to be distributed amongst the other capacitors. Well, the other ones, there's a C12. Let's write that up here. I've broken this down into the equivalent C12. Right? And that's in parallel with C3. If they're in parallel, that means that they have the same voltage across them. So if they have the same voltage across them, how much voltage is that? It's just 28 minus 16.8. So now I know that voltage 3 is going to be 28 minus 16.8. What the heck is that? 11.2. And if I know V3, then I can get Q3. Because Q3 is C3V3, so if you plug those in, what did I get for that? 44.8. There we go. So we're just working our way around. So the amount of charge stored on 3 is 44.8. And now I know that C1 and C2, I know that the voltage dropped across them both is 11.2. And they are the same capacitance, right? They're identical capacitors. So half the voltage has to be dropped across one and then half on the other. So V2 equals V1 equals 5.6 volts. And then I can figure out the charge. Q2, they're in series, so the charges are going to be equal. And so that's just going to be C times delta V. And C times delta, I already know the delta V's, and I know the individual capacitances, and what did I get? 22.4. Very cool. yeah, I guess I didn't have to, like, what if they were different capacitances? They're all the same, so that made it, I could just divide that 11.2 voltage in half. What if they weren't? What if they were different? Well, then I could figure out the charges across them, because across the combination, I know that the voltage was 11.2. So all I would really have to do is multiply the C12 combination by the voltage across them, and that gets me the charge across both. But the charge across both is the same as across either one, right? Because they're in series. So you could sort of work backwards to find your answer there. Okay, so this is what you do. If you have a network of capacitors, you just sort of work your way around. You figure out what the total capacitance is, and then the total charge in the circuit. That's always the first step. And then you start working your way around the capacitor in series and parallel combinations, just trying to see what you know and trying to pick off one and then the next one and then the next one. So, in a real sense, it's sort of like a detective game working your way around the circuit.